You don't have to wear a mask anymore?
It's up to you.
16.
Yeah, you don't have to. Yeah, until the next notice, because there are still COVID cases, rising COVID cases. Yeah. Yes.
Is there any pseudocode for the other?
All right. Let me not enable waiting room. All right. So we're gonna cover something slightly different today than what we have been doing so far. We have covered several search algorithms using free or graph search. In the last lecture, last week, we looked at minimax search, right? Where we assumed that we are optimistic, we're optimal players, and we assumed that our opponents basically are smarter, right? They're playing smart. And in order to be optimal, we would say that we were playing as a maximizing agent by maximizing our utility, while the opponents trying to minimize our utility. Not that intentionally minimizing our utility, but they try to maximize their utility, which is our minimization, because we looked at zero-sum games, right? Where one player's win is the other player's loss, right? So we looked at that scenario, and that was basically deterministic because we knew that we are playing optimal, and we knew that if we play certain action at every single step, we're going to know that our opponent is going to play a best action or an action that is going to be best for them, which will be the least basically beneficial for us, right? Today, we're going to talk about non-deterministic games. So we're going to add the notion of uncertainty, how basically games can be uncertain, or the environments where we basically don't know the outcome, or we're not sure. We covered 2 slides in terms of the backend agent, and there were a couple of ghosts, right, moving in the backend scenario. And in one scenario, we said that, okay, what if the opponents or the ghosts are smarter? What should we do? Should we just hit the ghost and just immediately end the game? What if the ghosts are just playing completely random, right? By being random, in very, very simple terms, you just assume or imagine that at every single step, you just roll a dice or toss a coin because you're not sure what you're going to do. Or your opponents, if they're random, you're not sure what they're going to do. So in very simple scenario, if for multiple games you can think of ghosts before they move, they just roll a dice or they toss a coin. If it's a head, then they'll just go right. If it's a tail, then they'll just go left. Or I should say, roll a dice. If it's 1, just go north. If it's 3, go south, etc., right? So we're going to talk about non-deterministic games where we don't know the outcome, and we're going to talk about the Expectimax. Slight variation of minimax. We're going to still talk about the, basically the idea behind Expectimax search is not very different from minimax, but because we are in a random environment, we don't know the exact outcome. We don't know exactly, or we know exactly where the goal is, but we don't know what our opponents will do. They're just playing random. So if they're playing random, what's going to happen? Because if they're playing random, there is going to be a probability involved. So we're going to talk about a few axioms of probability today, how we add the notion of probability, or how we see or how we should act in uncertain environments, which is the non-deterministic. Okay. Towards the end of this lecture, we're going to cover some basics of probability, what the probability is, how it plays a role in certain game scenarios, or not certain game scenarios, certain real world scenarios. And we're going to basically prepare ourselves for next 4 weeks. Actually, I should say the entire course, because we're going to talk a lot about the probability, about uncertain environments. We've been talking about quite a few scenarios in which we say that we know the goal. We know our destination. We need to go to Bucharest, right? Or we need to eat all the dots as Pac-Man. So we knew the goal, and we knew that what is the best or least cost solution. Most real world scenarios don't work like that. There is uncertainty involved, which is why we will have to talk quite a bit about probability. And then we're going to talk also about the utility functions, because our main goal is to design agents that should maximize their expected utility, right? Their benefit, and how we should assign utilities to the outcomes in our problem for our solution. That should be the most optimal. That should be the best. Okay. There are various axioms that we will have to follow, or various laws of probability that we will have to follow to make sure that our utility functions are calibrated, or the probabilities that we assign, they're calibrated. They're not just random. Okay. And then at the end, I'll just cover a couple of examples of what rational preferences are. You have to be rational as a rational player. Okay. So we will start basically with our example from last week. If you remember, we had this very small tree with a maximizing agent, basically the triangle, up-facing triangle. That was the maximizing agent, right? Or that is the player that we as ourselves play. And then we had a minimizing agent, right? Or a ghost. And then we said that there are some values, remember? The values that are assigned to the nodes, those are the leaf nodes, or those are the terminal nodes where the game ends, right? So assume that these 4 leaf nodes are basically the terminal nodes where the game ends, and we have the value. And then if you remember, we propagate the value up, and then we actually find the value of the root, right? So far, so good. We remember this example from last week. So for minimax, let's cover the same example for just a few minutes, and we will see how minimax is different, or how Expectimax is different from minimax search. All right. So for minimax, obviously what we did was, we are at the minimizing agent, we're basically selecting the minimum, right? We're using the minimum function, right? So for the left node, what we had was, we select the minimum of these two, which is obviously just 10 here, right? And then at the right node, we select which number from 9 or 100. 9, obviously, right? Then we just select 9. But then if we had alpha beta pruning, the moment minimizing agent sees this number, which is less than or equal to 10, then it will basically not just go in this direction, right? Because it was pruning, because the minimizing agent says that, okay, I found a number 9, and number 9 is already smaller than the number that I've already seen, because the agent at the top layer, the one layer above, is the maximizing agent. It will never care for this number, because we're playing the optimal, right? We're playing optimistic here. It will say, right, okay, the top agent, basically the agent above me, is maximizing. Therefore, it will not care for this number 100. It could have been 1,000. It could have been a million, billion, trillion, whatever. But we were playing optimal. We were playing as a maximizing agent. It's not going to care for whatever number it is here. As soon as it sees a number that is smaller than the other one, it's just going to stop, right? It's going to stop the game in there. And if it tries to play optimal, that is it. That's where basically it stops and says, like, okay, I am done at this point because my top agent is maximized. So that was basically the worst case scenario, because we're playing as in a worst case game scenario, right? We're thinking of the worst case, which is why we say that minimax algorithm, search algorithm, is only optimal if you're playing as an optimal player, right? Now, in random scenarios, so in here, for minimax agent, it's basically not going to care for this one. All right. But as I said, in random scenarios, suppose that your
minimizing agent messes up here, just does something that may not make sense, and it just will pick 100 for you in here. Suppose that we basically, instead of playing optimal, we say that there might be a case that our, opponent might just, mess up in somewhere there, right? So in that case, we are basically adding the notion of uncertainty. Another very simple example, let's pause it here. Another very simple example, I think I gave in the last lecture, and last week was that suppose that you've designed a very cool robot that basically, walks itself, goes to, from one building to another. Great, you have designed that, and you basically, allowed it to move its, actuators in a certain way that it should find using its GPS, and it just finds the shortest path possible from one building to another. Let's say from College of Education to Jack Brown Hall, right? That's great, and you will expect it to just work perfectly. But what if the environment doesn't play, according to your expectation? Suppose if it is windy outside. Suppose if there is when it was walking, there's a muddy hole right in front of it, right? It has to take a turn right, and then just change its path, right? So then you're basically, your robot is still trying to be optimal, but not according to your expectation, because these are the situations in which are not under your control. Then the environment plays a role, right? That is something that is not in your control. In that case, you basically have to, look for what kind of, scenario you're playing in. You basically are not going to play as a worst case scenario. You're adding the notion of uncertainty. And in very simple terms, we're going to start with the average case. Okay, average case. Because just because we don't know what the environment is going to do with us, or what the expectations are, we simply add the average, or if being uncertain in a very, very simple scenario, we're just going to do the average case scenario. So now suppose that your maximizing agent knows that your minimizing agent plays randomly. By randomly, let me just, very, very brief or simple definition. Playing randomly means that at every step in your problem, or the solution that you have designed, at every step you are rolling a dice, or you're tossing a coin, because you don't know what you're going to do, right? So in very simple case scenario, suppose that your maximizing agent knows that your minimizing agent basically is playing randomly, not playing smart. Then in simple case scenario, you can think of something like this, right? All right, as a maximizing agent, now that I know that this minimizing agent plays random, there might be a 50% chance that it might go left. It might choose this branch, or there is a 50% chance it might choose the right branch, right? Suppose that this is the very, very simple case scenario that we're covering. That is just random. Minimizing agent is random. So if we are saying that it's just like 50-50 chance, then all what we are doing is simply averaging these numbers instead of selecting the minimum, right? So what is the average of these two? It's either 10 plus 10 divided by 2, which is 10, or 10 times 0.5 plus 10 times 0.5, which is again 10, right? Here, 9 plus 100 divided by 2, which is 109 divided by 2, which is 54.5. In that case, your maximizing agent basically will prefer this one because it is better than 10, right? So you see, maximizing agent is only assuming that the minimizing agent is not playing as a minimizer anymore. Minimizing agent, it's just playing random. But the maximizing agent is the same, still the same. It will pick up the maximum, right? So what you're doing is you're basically adding the notion of uncertainty, just because in this case is that it's the average case, not the worst case. That's the only difference between Minimax and Expectimax search. No, and Expectimax search. So you do expect Imax, just one word, expect Imax, Expectimax. Okay, so what you're doing is the difference that you are adding, introducing in the Expectimax search is that uncertain outcomes are controlled by a chance node, not the adversary. Because in Minimax, you are saying that this minimizing agent is going to maximize its own utility by minimizing my utility, right? So you're not treating the minimizing agent as the adversary anymore. You're basically adding chance. So at every minimizing node, basically you're adding a chance node. And how do you do that? So to convert Minimax search algorithm to Expectimax, all what you have to do is you just replace the down-facing triangle with a circle. Okay, that's it. You're done. Minimax search has been converted into Expectimax. That's all. Isn't it super simple, just straightforward? You just convert your tree, wherever the down-facing triangle is, just convert them with a circle. But that's not only it. There is a little bit of coding involved, programming. I'll show you, okay? Where first of all, in Expectimax, we are actually adding unpredictability because now your minimizing agent is not the minimizer anymore. It's a random variable. You're actually, basically, you're adding unpredictability, which means that the result of an action is unknown. You're not sure what the result would be because you're expecting your minimizing agent to be unpredicted. So first of all, we add a chance node instead of a minimizing node, right? A chance node instead of a minimizing node. And we assume that at every step that the minimizing agent takes, they're just rolling a dice. All right? They're just rolling a dice, and there is an explicit randomness that you have involved. Basically, at this layer, you are adding an explicit randomness, okay? Because your opponents are unpredictable. The ghosts respond randomly, and actions can fail, right? As we just said that if your robot is moving from one location to another, going to its destination, there might be a chance that it might face an obstacle in its shortest path. Then it will have to change its path. There might be a chance that the wind might blow it away from, the actual direction that it has to take, right? So actions can fail too. So the values in Expectimax, they should reflect the average case, not the worst case. So the difference between Minimax search and Expectimax search is that one is the worst case because you're thinking of the worst case. What is the worst case that can happen to you? In here, you're just looking at or expecting the average. Okay, so you're looking at the average case. So at every step, we are computing the average. Okay, so max node, the maximizing node is just the same as in Minimax, but the chance nodes are going to replace the minimizing, agent, just the chance node. And these are the chance nodes because we are adding explicit randomness in our tree search or in our game. Therefore, we're adding uncertainty, which will take us to Markov decision process. It's not week 5, weeks 4 and 5. It's going to be weeks 6 and 7. We're at least 1 week behind. So I'll try to fix that part in the syllabus because we are running. We're running behind because of a 1 day off and also the flooding event. But we're gonna by looking at the probability today, we're gonna be able to just move to Markov decision processes. That is going to be week 6, and then we're gonna move on to reinforcement learning. The reason why we're going to do the reinforcement learning after Markov decision processes is because MDPs are the foundations of reinforcement learning. We will have to understand what Markov decision processes are before we move into super, super advanced reinforcement learning topics. Another thing is that I hope that this happens before we get to the reinforcement learning part. I've actually ordered a robot, the ant robot, and we're gonna implement reinforcement learning algorithm to teach the robot to stand up, start walking, and then start running automatically. Ant robot. It's gonna be an ant with four legs. So it's actually arriving from Europe. So I don't know how long it will take. I have ordered it more than a month ago. It's really small. It's really small and it has four, well, it's not long, it's just like rectangular. So it looks more like an ant than a dog. So hopefully we will get that in time so that we can, we can teach it without providing it any explicit input. We're not going to tell it how to stand. We're not going to tell it how to run. We're not going to tell it how to walk. It's just going to learn, itself by interacting with the environment in many simulations. That's the beauty of reinforcement learning. Yes. Yeah. Ant. A-N-T. Yeah. Real ant. Its official name is real ant. But I'll talk about it. And then I will basically, welcome all of you if you are interested in doing something else with it or use reinforcement learning with something else. So stay tuned. Next 4 weeks are going to be really interesting. We're going to have, we're going to look at the Markov decision processes. These are any real world problem can be solved using MDP. Any real world problem that you can think of, it can, if you can formulate it into a Markov decision process, then you're able to solve it. And we will solve several real world problems using MDP and reinforcement learning. Okay. So what we said the last week was, so if in this scenario, if you remember, if we are playing as minimax, optimal in minimax, if you were optimal, if you look at this scenario, then as a Pac-Man, the best move was to just hit the orange ghost and finish the game. Because every single step that you make in the Pac-Man, it's going to give you a score of -1, right? And your job is to end the game with the highest possible score. So instead of randomly moving without being able to eat, you just immediately hit the ghost and that's it. Plus the game, explode, that is it. So that you can still get a better score than this, right? So that was the optimal, worst case scenario. What happens in the Expectimax search, because, now remember, because we assume that these ghosts, these cute innocent with big eyes, two ghosts, we're now assuming that every single step that they are making, they're rolling a dice. They don't know where to move. They're just playing random. If they're playing random, then if you might play several games, several situations, there might be a situation in which this ghost might actually go in this direction, right? Because we're assuming that they're playing randomly. Then in that case, the best move would be to still go to the left, because now you're assuming that the ghosts are playing randomly, and there might be a chance that this blue ghost will go down and towards the right. That's still the best move. That's the difference only between Minimax and Expectimax, because in here we, instead of ghosts, in more general term, you say the opponents play random. Okay, so let's look at the algorithm. Let me clear this these arrows. One second. Oops, there are quite a few. All right, so the algorithm for Expectimax is actually very, very similar to Minimax. So if you remember the value function, our value function, just like Minimax, just like how we covered in the last lecture, that if the state is terminal state, return the state's utility. Because we already have the utility, we already have the value, right? Because it's a terminal state. We have reached the end. Okay, that is it. If the next agent is max, return the max value. That's exactly the same as minimax subshell, if you guys remember, right? If the next agent is Expectimax, instead of minimax, instead of minimizing agent, return the expected value. Okay, instead of minimum value, instead of using the minimum function, you use the Expectimax. So look, the left side is exactly the same. Maximizing agent is not going to change. Okay, it's exactly the same. Perfect. Here, we're going to change a little bit. Now, because we have added the probability, so instead of working on the minimum value, here we're looking at the probability. So we have the probability for each move, possible move. Here, the probability, if you are just simply thinking of rolling a dice, the probability for the 6 different actions, possible actions, 1, 2, 3, 4, 5, 6, right? So you get the probability with which number 1 will appear, probability with which number 2 will appear, probability with which number 3 is, it will appear. It's going to be just 1 by 6. If you're thinking of just very simple scenario, right? That's just the average. And then what you do is you get the values like 10, 10, 9, and 100, the leaf nodes, and you just simply multiply them. Just like how I did in the previous slide, 10 times 0.5 plus 10 times 0.5. And then we just get the value. Okay? Instead of getting the minimum, we get the probability that with which each node basically is associated, and then simply multiply them with the value of the node. That is it. That's the difference between minimax and Expectimax. So what we do is for each successor, something like this. Look at this. Look at this node. Because at Expectimax, we now have with the arcs, we now have the probability associated. So something like this, that at Expectimax, there is a 50% chance, 1 by 2, half the chance that it will select this one. There's a 1/3 chance that it will select this value. There's a 1/6 chance that it will select this value. Now, suppose that if this was minimizing, suppose that instead of the circle node, it was a minimizing agent. Which value, which path do you think it will have chosen in minimum? -12, because it's a minimizing agent. It will always pick up the minimum value. But now what we are doing is we're just adding the notion of probability. Something like this. Suppose that your robot is standing. Suppose this is a happy robot, smiling robot. Now, what we are saying is that suppose its destination is right here. Okay. It can take either go, forward, it can take left, it can take right. Okay. It says that there is a 50% chance or 0.5 that it will go forward. There is a 1/3 chance that it will go left. 1/3 chance is 33%, right? 0.3333. Let's just end it here. And there's a 1/6 chance, which is 66666 somewhere where it ends, right? So before I explain that, let me go back to the slide and let me tell you something. I'll get to that. I'll get to that in just a few seconds. So we had v equals -infinity in the maximizing agent because we were always thinking of the worst case scenario, and we had v equals +infinity for the upper bound, right? Here we're initializing v equals 0. Does anyone have any idea why we have initialize V equals 0 for the probabilistic environment. Exactly. Okay. How many of you have ever taken any course that had something to do with the probability? Oh, quite a few. Okay. So there are some well-established laws of probability that you will always have to follow. We don't have to prove them because they have been proven, for decades or even for centuries. Today, let me just cover 2 laws that we will have continue to follow in this entire course, because those are the basic laws of probability that we have to follow. The first law is that the probability of an event can never be below 0. It's never going to be below 0, which is why this is the worst possible case, that there is a 0% chance that something will happen. Okay, so that's the first law of probability that we will have to follow, that the probability of an event can never be in minus. Okay, can never be less than 0. The second law of probability that we will have to cover, we will have to talk about quite a lot, would be that the sum of the probabilities that we have associated with certain events, it will always have to be 1. Okay, the sum of all the probabilities for all the events, something like, the robot can either move, forward, backward, left, right. These are the only 4 possibilities that we can have. Now, suppose that if we have said that there is a 50% chance that the robot can move forward, there is a 20% chance that the robot can move left, and there's a 20% chance that the robot can move right. So that's 90%. We're still unsure of where is going to be the next, the other 10%. It might just fall, or it might just go backward or something. The actuators might just mess up. It will have to go back. So the sum of the probabilities will always have to be 1. So these are the 2 laws of probability that we will have to follow for this entire.
So we can still have an expected value of V of a negative number, right? Value is negative.
V can be negative, but the probability. So you see, we have 2 things. We have P and we have V.
Yeah, I was just saying it can still be negative.
Yeah, V can be negative. V can be negative. P cannot be. Okay, the probability cannot be negative. Run it. Some of the probabilities, suppose that you have certain events, a random variable, certain events that they can possibly happen. So we assign them a probability, right? Each node a probability, something like this. You see here, 1/2 plus 1/3 plus 1/6. They have to be equal to 1. So if we sum all the probabilities for all possible events that we have, it will have to sum up to 1. Okay, it cannot be lower than 1. If it is lower than 1, then you are still in a partially observable environment. Okay, so we're gonna talk more about it. I'm gonna cover a few examples, but you see here, every time when we assign the probabilities, the sum of those probabilities has to be equal to 1. Right. Okay, so here, what we are doing is, you see, we get the probability, right? 1/3, right? And then 1/2, 50%, and then 1/6. So this is this step that we have already taken. Then we get the value. So you see here, V plus equals. This is simply doing this, okay? 1/2 times 8 plus, you see here, V plus equal, plus 1/3 times 24 plus 1/6 times minus 12. And the answer is 10. Okay, if you do this, calculation, the answer basically becomes 10. Okay, so that's what it's doing, those 2 lines. We're getting the probabilities, and then we're just summing them together. All right, let's talk about something very important here. Expectimax example. Remember in Minimax, we said that it's an exhaustive DFS, right? It's an exhaustive DFS, which basically goes in every possible direction from the leftmost possible node, blah, blah, blah. And then we would select the minimum, right? Like 3, and then 2 from here, etc., etc. Suppose this is an average case. We're just simply doing the average. What would be the value in the first circle node? what would be the value? 3 plus 12. Okay, I'm gonna do it here. 3 plus 12 plus 9 by 3. Yeah. 8. Oh, yeah. How about here? 2 plus 4 plus 6 divided by 3. And here, 7, right? Like this. If it was minimax, it would have worked something like this, right? So we select 3, right? That's the minimum. Then we select 2, right? As soon as we select 2 in here, we see that 3 basically is greater than or equal to 2, then this would have been pruned. This would have been pruned, right? What we're doing in here is that we're looking at the average. Can we do the pruning in here? Why not? Exactly. Okay. Every single node in here, every single node is either likely or unlikely with a certain probability. So we cannot exclude or ignore any node in here. Suppose that we have selected the average here, which is 8, right? As soon as we get here, what if this number was 1,000? What if this number was 5,000? Then this average would have been much larger than this one, much greater than this one. So we cannot do pruning. Remember, we said that in minimax, using alpha beta, in minimax was this, right? B to the power m. Then with alpha beta pruning, we had b to the power m by 2. We could have reduced its time complexity to, almost half the tree. We cannot do that with Expectimax search. It's not possible because every single outcome is either likely or unlikely. Sounds good so far? So what we're doing is, suppose that we have a very simple, game scenario where we have our Pac-Man and we have this guy over here. Oh, they look weird. So the tree on the left is actually representing this scenario. We have one maximizing agent, our Pac-Man, and we have 2 ghosts. And how we can add multiple opponent players or multiple players, we simply just add layer by layer. So the one basically is a ghost 1, and the other one is ghost 2. All right. So remember, we said that the deeper we are in the tree, the better the value is, right? Because we actually know the outcome now, because we are all the way at the deep. But for very, very big trees, we just would run depth limited, right? But if we run depth limited, the problem with that is we will have to estimate. We'll have to provide the estimate of the true function, right? In here, because we don't know, we're not even going all the way to the depth. Whoever is sleepy, just go splash water on your face and come back in 10 minutes. You can leave the room for 10 minutes. Yeah. Depth limited. Okay. You can go, because your tree is really, really large, all right? Meaning that if your tree is really large, you cannot go to the leaf nodes. It's not possible, right? So what you do is basically limit the depth, and then you estimate the values. Just provide an estimate. And remember, we said that evaluation function, we will have to select the best evaluation function. That means we will have to estimate, provide the estimates here, right? Those estimates might not be super, accurate. Suppose that in here it was, the actual value was 492, and here it was 362. You may just come up with the estimates, something like this, using an evaluation function. I'll talk about the evaluation function, in a more detail, but what we do is estimate what the true Expectimax value would require a lot of work to compute, a lot of work. Okay, and let me just show you an example. Right after explaining just the probability for about 2 or 3 slides. Okay, so in this entire course, we're going to talk about the probability from a random variable perspective. How many of you you know what a random variable is? Don't look at the slide. A random variable is basically an event whose outcome is unknown, whose outcome we don't know. It can be an object, okay, whose outcome we will not know. Typically, like in terms of the probability, a random variable is considered as an event whose outcome is not known. An event can also be, you know, an action. Based on an action, you get a value or something. It can be an object, but we'll talk about from a simple, you know, explanation. We'll talk from there. Suppose that in a very simple case scenario, suppose that I live in this area and I have to go to Ontario Airport. Okay, and you know, I assign probability. I think that, you know, my probability looks something like this. There might be no traffic if I'm going to the airport. There might be light traffic. There might be heavy traffic, right? So remember, relaxed problem. Relax. I'm relaxing the problem right here. For you, the probability might look totally different. You might think that what does even none, light, and heavy even mean? What does it even mean? I don't understand. I understand traffic in terms of like how many number of cars per 50 meters, how many number of cars per 100 meters, how many number of cars per 10 meters from the route that I'm going to, right? And then you average those, and then you say if the number of cars per 10 meters or per 50 meters is let's say 20 or something, then I'm going to consider it as you know, medium traffic, something like that. If the number of cars per 50 meters is only 2, then I'm going to consider it as none. You can assign basically utilities, or you can have the probabilities based on what your problem, you know, what your problem is, what your scenario is. But for the simple case, let me just consider that there are three possible values or 3 possible scenarios where I say there's no traffic, light traffic, or heavy. Okay, so a random variable is an event whose outcome is unknown. Probability distribution is the assignment of each of the possibility is the assignment of a value. That's a probability distribution. Something like this: PT equals none is 25%, T equals light is 50%, and T equals heavy 25%. Remember, probabilities are always non-negative, and the sum of the probabilities have to equal to 1. Those are the 2 laws that we have talked about. In this course, just because we are starting with the probability now, we're only talking about traffic either no, there is a light traffic, or there's a heavy traffic. But what we are going to talk most about in this course is given some more evidence. Now, I say that there is no traffic, light traffic, or heavy traffic. What if it is 8 a.m. in the morning? If I'm providing more evidence, like probability of T equals heavy, given that I know that it is 8 a.m. in the morning. So then your probability will change. Then the probability of T equals heavy will shoot up to all the way to 65%, because 8 a.m. is, let's say, the peak hour time, right? There is a lot of traffic at that time. Then it will be something like this. Here, it will go down, and it will be something like this. So your probabilities will change as you provide more and more evidence. That's what we're going to cover quite a bit. With more evidence, probabilities may change. Okay. I'm going to say, I think in the next coming few slides. Okay. So let me read this, and I'm going to expect that it might not make sense, which is okay. The expected value of a function of a random variable is the average weighted by the probability distribution over outcomes. Make sense? A little bit? Okay, confusing, right? Quite mouthful. Expected value of a function of a random, what the heck, of a random variable is the average weighted by the probability distribution over outcomes. Quite mouthful. You know, all what I'm doing is I have a probability distribution, right? It says random variable is the average weighted by the probability distribution. So I say that if there is no traffic, then it's going to take me 20 minutes to get to the airport. If there is light traffic, then it's probably going to take me 30 minutes to the airport. If there is a heavy traffic, then I'm going to assume that it's going to take me an hour to get to the airport. And now that statement, all what it's saying is, you see here is an average weighted by the probability. Remember P times V? Probability times the value, P1 times V1 plus P2 times V2, all the way up to Pn times Vn. So what I'm doing is I'm multiplying probability, and then I'm just doing the sum. That's all. That's what this statement says. Okay, something like this. I'm multiplying, and then I'm adding them together. And then you're going to have your result, right? Like about 30 minutes, 35 minutes. That's the expectation. So we're going to have the expectations, right? That's just the average, another way of doing the average. Expectation basically is the average. Okay, so let's just very briefly talk about what probabilities to use. Where are we going to get these probabilities from, right? It can be based on the expert judgment. You may have gone to the airport around 8 a.m. to the Ontario airport for quite a few times, right? And from your past experience, you think that you believe that, yes, at this time, the traffic is going to be heavy, right? Or you can use a sophisticated model to come up with the probabilities, like Google GPS. It basically gets all the historical data around 8 a.m. And then you say like, okay, if you set the departure time, it will actually calculate the value and say it's going to be anything between 45 minutes to an hour and 10 minutes, something like that, because it's actually using a quite sophisticated model to calculate those probabilities. You can also do that. In our course, we are going to do the both. Okay, we're going to use a model, develop a model from scratch. We're going to get those calibrated probabilities, and then we're going to use those. And in some cases, we're going to use just expert judgment, some domain knowledge. Just like the heuristic, if you remember in the search problem, somebody just, some guy came and just gave you the actual distance and say, okay, this is the best possible, route that you can take. You can either use like, some domain knowledge. All right. So we will assume that each chance node comes along with probabilities that specify the distribution over its outcomes. Okay, something similar. So let's just have a quiz, very quick question about the selection between minimax and Expectimax. Suppose that you know that your opponent is actually running a depth 2 minimax. Depth 2 minimax, like go down 2 layers. Using 80% of the time as minimax search, algorithm, and then moving randomly otherwise. 80% of the time it's minimax, acting as minimax, and then 20% of the time it's acting as just random. What tree search do you think we should use? Minimax or Expectimax? Why Expectimax? Still 20% chance that it's going to be, random, right? Plus, another good point is you can always use Expectimax even with minimax, with the probability of 1. So at each point in here, if you are, I'm actually in a listening mode for some reason. Okay, let me share that again. All right. In here, you can assign the probability to 1 and still use Expectimax. That will just be like Minimax. Okay, so the answer is basically Expectimax search. Now, if we are going to the depth 2, somewhere in here, then there is a much. Remember, we talked about the issue. I think in the last lecture that suppose that we are thinking that our maximizing agent is optimal. Our opponent might also be optimal. They might also be thinking that what we might do in the next step, right? Just like I'm thinking of what Sophia is thinking of, what she is going to do. I'm thinking of what Sophia is thinking of what I'm going to do as next. We'll have to put a stop at it somewhere because it's going to keep going over and over and over, and it's going to complicate more and more, which is why getting the values in here, because your Expectimax might still think that you are also the optimal player, and you have to run a simulation of the entire game at every step. If you're doing that, it's going to get more and more complicated. We'll have to put a stop, but we will talk about it in just a few minutes. Now, suppose that we have our random ghost. If we have the random ghost, you see, the Pac-Man is still actually coming towards the dot because we know that the ghost basically is playing random, and there might be a chance it might just go away. It might just go away because it's playing random, right? So in Expectimax search, it is still a better move to just come closer to the dot because we know that this guy is playing random, and it just might go in another direction. What if it was Minimax? Well, now we know that if we are going to go closer to the dot, this guy is going to come after us because this guy has just been brainwashed. Somebody told it that you are its worst enemy, and you just have to run away from it. And it's going to come after you to eliminate you. So in that case, you're playing the worst case scenario. You will have to just go away, distract it, go behind the wall, hide it a little bit, whistle at it, and then just run away from it. And then just come back and eat the dot, right? Even though this is not the most perfect scenario, but as an optimal player, you still have the winning scenario, right? Expectimax problem. What if it was Expectimax? Pac-Man, it will still basically, the Pac-Man will still come closer, and it will find out at the next step that the ghost basically, you see that the ghost, instead of going this way, it came this way, and then it just turned away. Because it's every step it is doing the computation. Okay. All right, how many of you know the game of backgammon? Have you ever played the game of backgammon? It's been a while. Okay, so what happens is there are two players, right? And you have to just arrange basically your things in a certain order. But before you make a move, you have to roll a dice, right? You have to roll a dice. So now it's not just only you and your opponent. You, as well as your opponent, will have to make a move after you or your opponent will roll a dice. So that means there is an environment that is also playing. So your move or your opponent's move is dependent on what the dice will come up with, right? So you actually have an unpredictable, another variable that basically is the environment. So you are the maximizing agent, then you have the minimizing agent, but between those, you actually have a random variable. That's the environment. You're dependent on that. You're not sure of what move to make before you roll a dice. So the environment basically is an extra random agent player that moves after each minimax agent. Okay, so basically those are the mixed layer types. What if we have mixed layer types? Yes, we can still have that. Here, in this case, we will have the minimizing agent. We will just simply do exactly the same as what the minimizing agent does. We'll select the minimum values from here. And then at the top, we'll just get the average. Okay, we'll get the average here, explicit randomness, and then here we'll get the maximizing agent. We can complicate this game by adding, minimizing, maximizing, as well as an Expectimax for mixed layer types. Sounds good? Okay, just a few more slides, I promise. Okay, we have been talking quite a lot about zero-sum games or two-player game. What if there are multiple players? Sorry? So what if there are multiple players? What happens when you have multiple players? So in Expectimax, when we are random, we're not going to care about the opponent anymore. We're not in the worst case scenario. All what we're going to care about is our own maximum expected utility, right? We're going to maximize our utility by ignoring or by not caring about what the opponents will do because there is randomness, right? You're not sure. So there can be multiple players too. What if there are multiple players involved? Okay, now suppose that Sophia and Nathan are playing a game. Okay, by no means I mean that you guys look like this, but it's just the curtains, okay? So suppose that Sophia and Nathan are playing a game, right? These are multiple players. And now suppose that the third guy is Ronald, looking at right there, right? So, yeah, it's not a very good sign for them too, but it's just a random game, right? Okay. So what happens is in multiple players, all what you have to do is wherever your turn is, you're gonna worry about or be concerned about your outcome. Forget about what the other players are. Okay. Suppose that this is the green, or this is Ronald's turn in here. Now keep in mind that this is a maximizing. All of them are maximizing. So they're red, blue, and green, right? All of them are maximizing. And suppose that this is Ronald's turn. So from here, which node do you think Ronald will pick? The left one, right? Right? Because here, the utility for Ronald is 2, and here it's 6. Right? So it's going to pick up this one. Right? Now, Nathan can sit and cry for an entire day of why Ronald did not select this one, because Nathan could have had 7 in it. But the problem is, this part is basically under Ronald's control. Nathan or Sophia do not have any control over it. So at every level in multiple players games, the player that is going to make a move is going to be only concerned about its own utility. Forget about other players' utilities. That is it. Okay, they're just going to maximize their own utility. All the way to the right here. Where do you think Ronald will pick which branch will Ronald pick in here? The right one, right? Again, it's a loss for Nathan because here it's 5, and here it's 7. It's a loss for Sophia too. Here it's 7, but here it's 2 for her. But the problem is that it's this move is controlled only by Ronald. So in this case scenario, you're going to just look at or worry about only your expected utility, not other players or not the opponent's expected utilities. Okay, so let's talk about the last part. Where do utilities come from? How do we know that such utilities even exist? Okay, let's talk about that part and let's finish. Suppose that we have this scenario. Okay, the maximizing agent basically will select 0 from the left, right? Minimizing agent will select 0 from the left, and then it's going to select 20 from the right branch, right? And then basically, 20 can be the best possible move that or value that the maximizing agent can have, right? So here it's 0, here it's 20, and then what we will get is 20. Now suppose that if it was Expectimax, what happens now? Now remember what utilities to use. Now here, this is basically 0 plus 40 by 2, which is 20, right? This is 50 by 2, 20. So that means maximizing agent will prefer this, right? Right? But now suppose instead of suppose that that utility function was x with these values 0, 40, 20, 30. Suppose that we just square them. Suppose we use x squared instead of x. So you see here 0, 1600, 40 squared 1600, 20 squared 400, 30 squared 900. Now let's see what happens. Here, this is 1600 by 2, which is 800. This is 1300 by 2, which is 650. Uh-oh, there's a problem. Just because we used another utility function, we used x squared instead of x, there is a problem. The utility or preference has changed. So we have to calibrate our utilities, and we have to make sure that we are using the right utilities in our game. If you mess up with these utilities, you're going to have bad results in your problem. Okay, and those utilities can basically, can be calculated, using various different ways, but there are several axioms. There are several axioms of rationality that we will have to follow. If we follow all those axioms of rationality, then we're going to make sure that we are optimal. We're going to select the best utilities possible. Let me just show you a few of those. Okay, the preferences. We will have to prefer something over the other in order to make sure that we have the right utilities. Okay, something like this. So you see, suppose that, lottery, no matter how much you like or hate lottery, it just has to have, certain events of either winning or losing, right? So suppose that if you just participate in a lottery and there are prizes like prize A, that you win the lottery, and B, that you lost. That's your loss, right? A or B. Then there is a probability associated with winning, and then there is also a probability that you might lose. There is a probability P that you will probably win, right? A means win, and then there's a probability that you will probably lose, which is B. A is win and B is loss. And P, there's a probability that you might win. Why is there 1 minus P? Why is there 1 minus P?
That represents the remaining ability, the probability.
That you may lose, right? And if you sum P with 1 minus P, it will have to be equal to 1, right? Because you see here, P plus 1 minus P. The sum is 1. So we'll have to obey the second law. Okay, so suppose that you have a prize A, and from your Expectimax, there is a certain probability that you will lose. There is a certain probability that you will win, and there is a certain probability that you will lose. You will have to find basically prefer one thing over the other, and there are a few axioms that we will have to be very careful about. So let's just talk about it for just 2-3 minutes, and then that's it. We're done. Okay. So preference, meaning that if A is better than B, then you will have to prefer A over B. Okay. Obviously, winning is better, right? So we'll have to indifferent. They're just not different. You just pick either A or B. It's just going to be the same uniform distribution. Okay. Let me see. Let me just show you this. So first axiom that we're going to cover is transitivity. Look at this. If A is better than B and B is better than C, then you will have to prefer A over C. Then A has to be better than C. You have to follow that. What if you don't follow that? What if what if you don't have basically a transitive preference? Let's see what the problem with the intransitive preference. Now suppose that if B is greater than C, which is correct, right? B is better than C, then that means then agent C will pay an agent 1 cent to B, which is this. C is paying 1 cent to B, right? Because B is better than C. Now, second thing is, if A is better than B, then B has to pay 1 cent to A, which is B, this one, right? Which is good. But now suppose that you're not obeying or not transitive, and instead of A better than preferred over C, you say C is preferred over A. Then A will have to pay 1 cent to C, right? And then you will just run in the loop forever, just passing 1 cent forever, and you're not preferring. Your game will never end. Your problem will never be solved. You'll have to be transitive. There are a few others. that we will have to remember, we'll have to be very careful about. Even if you're designing, once we get to a point where, you have these ant robot and you just basically, designing an algorithm for it, you will have to remember the basically axioms of rationality. What is rationality, by the way? Do the right thing. Do the right thing. Basically, do something that is in your own best interest. That is the most beneficial to you, right? So axioms, do something, do the right thing. Okay. So orderability, you say that if A is preferred over B, or B is preferred over A, or they have to be indifferent. Right? Because A is just like, both equally likely or equally unlikely or unlikely.
This is in the, A is better, A is not better, B is not better.
No, it's or. It's an or sign. So if A is better than B, sometimes B is better than A, then they have to be just indifferent. The two of those.
Oh, that's what I'm saying. The last four on the order. Because if A is better than B or B is better than B, then they're the same, isn't it? Right.
A is better than B. The orderability, we're talking about the orderability.
The last four.
No. So it's or. So you see, sometimes A is better than B, or B is better than A, or they have to be indifferent. Or they have to be. It's just it doesn't imply. It's right now. It's not implying. It's just the three possibilities. Sometimes A is better than B. Sometimes B is better than A, or they have to be indifferent. Or it's an or operation. Transitivity, we just talked about it. Continuity. If A is better than B, so suppose that if A is the best outcome, that you know, and C is the worst outcome that you know, and B sits in somewhere. Then that means for all possible A or C actions, basically there has to be a probability that A basically the best outcome, or C or B might have to be indifferent because it just sits in between them. These are a little different. I'll just explain those in the form of probabilities. In the next coming lectures. Okay, but these are some of the ones that basically that you will have to follow. Monotonicity, super simple, straightforward. If A is better than B, okay, then you should prefer lotteries that have more A's than the lotteries that have less A's. That's all what it's saying. You see here, P is a probability that A occurs, Q is a probability that B occurs. So the probability with P should be just preferred over the probability with the Q. So if A is preferred over B, then you should prefer lotteries that have more A's than the lotteries that have less A's. That's the monotonicity. If you achieve all of these, then basically you have the stamp of rational preference that you are rational. Okay, so if you have all those axioms of rationality achieved, then you have actually a stamp, a certificate that you are rational. Okay, I wanted to cover some of this, but just one more slide. Human utilities. Okay, which best possible price. Suppose that you have a best, basically compare the price to a standard lottery. Obviously, everybody would want to, get paid $30. Everybody would like to do that, right? Who doesn't like money? Now, suppose that you have this scenario. So in terms of the human probabilities, would you like no change or instant death? Which one would you like? Obviously no change, right? So you will basically have to, assign the probability. There might still be a million or billionth chance that this might happen, instant death. but you will have to basically assign these probabilities based on the rationality axioms that we will, have to follow in several of our lectures, upcoming lectures, okay? I wanted to talk about, the prize money and how, these insurance companies basically, give you the benefits, and it makes, you feel like, oh, there's a lot of benefit in it. But that's how they play basically the games, and how they, they basically let you believe that this is the best outcome for you, but it's also the best outcome for them too. But I wanted to explain, but we're actually 4 minutes over. I'm gonna stop here, gonna stop recording. If there is